Yeah, so I'm Chris. After finishing my master's thesis, I turned it into a paper and submitted it to ACADIA. ACADIA is one of the larger digital design, digital architecture focused conferences, specifically focused around fabrication. And this particular conference was focused around the idea of design agency. So the idea of designers using software in order to actually produce new and interesting ideas and strategies. So presenting at that was fantastic. So I met a whole bunch of interesting people. Got to see Hadid, which is kind of cool. The crux of this is that when I came back, there was a lot of information that I really wanted to spread, and so we presented the stuff at the Wellington Revit user group, and got very good results. And so I'm up here to deliver this, and then down in Christchurch, hopefully, to deliver it again. In terms of my background, at university, I sort of fell into Grasshopper and fell into parametric design in sort of a big way. Made a couple of things. On the right there is an exhibition that we put on in Tokyo, and this is entirely parametrically generated sort of timber structure. Did my master's thesis on procedurally generated buildings, which was a thing, and so this is what got me into ACADIA. And so I want to start off this talk, we're going to be running through a lot of the stuff pretty quickly. It goes from the urban scale all the way down to the material scale, and so I'm just going to sort of shotgun you guys with this stuff. I'm going to open this with this quote, which hopefully you can read. Far away, who's got the glasses on? The next step in our technological evolution is the use of design computation, software programs that use algorithms to link geometry with data to address specific problems. And that's Paul Odsley, who's the Principal Director of Design Technology at NBBJ, which is a big American firm. So I want to start here with one of Kay's houses buildings. The reason I bring this up is because this was sort of the poster boy for Revit for quite a while. And while it was documented in Revit, it was actually made with custom tools that Kaz and his design group sort of built themselves. This wasn't a one-off thing. This wasn't something that they were attempting. They just tried this and then threw that information away. This triangulation routine that they use, they've developed it, and it sort of defines everything that their firm is doing. So the key thing to look at here is just the fact that they're building tools in-house, custom tools, not relying on anyone else's, building it in-house and then using it project after project after project, and using that to build up momentum and using it to build up a broad range of things that they can do. So everything that I'm going to cover today is basically within the grasps of anyone. That's half part of the reason I want to do this. It's done with Rhino and Grasshopper, or it's done with Revit and Dynamo, or it's done with Rhino and Dynamo and Revit, or it's done with any other combination of those things. Dynamo and Grasshopper, they're both visual programming languages. They're both quite intuitive, and they're both free plugins for the software. So if you have the software, you can download Dynamo, you can download Grasshopper, and you can use it. These tools are getting more and more focused on allowing multiple users to influence with them. This is an NBBJ workshop that we went through. What you're seeing here is 3 Grasshopper definitions. All of this is in the cloud. Each one of these little modules of code was on someone's home machine, and we were sitting across the tables from each other. And as we were collaborating, and we built this thing in about 45 minutes through that collaboration. So that's everything from the initial form down to the individual panes of glass on the windows. All of that was done in 45 minutes. Any tweak to any of those has like a ripple down effect that comes all across it. And you could have as many people as you wanted working on this at once. It would update live, and it would work. And it works better than you think. So I'm going to start at the top with just analysis and planning. These things here, these 2 images here, these are two maps, purely screenshots out of Rhino. And the reason I bring them up is what you're seeing on the left is red is there is no access to churches, blue is there is high access to churches. This is just one of 1,000 maps that could be easily thrown up in order to do urban analysis. On the right there as well, these are screenshots straight out of Revit, straight out of Rhino. This is just one of the tutors who was at that conference, and basically what he was trying to show off was the fact that this kind of analysis can be done live. If you're sitting in a meeting and someone is asking, what access do I have to this? If you've got open maps or Google Maps access and you can pull out down those databases, you can draw information live in real time, and you can actually use this to drive your design process. Again, this is at a much smaller scale. This is individual sightlines of individual office windows. and this is a map of Seattle with basically exploring whether or not rooms in this building have views of the Space Needle. And so as this thing is being manipulated in real time in front of the client, they can sort of see, okay, if we change this, these offices have different views. This office has views over here. This office has views over here. That kind of thing. So it's all this stuff is happening live. This stuff is also becoming more and more. This is a website called Google Flux. So it's becoming easier and easier to access. What Google Flux is it's a live planning tool. It's showing you all the planning conditions that drive a specific space in real time. So what you can actually do is get all of that planning stuff visualized so that you can interpret it as well. And when you start thinking about, okay, this is what Google is doing, but you can actually do this on a small scale, and you can do it on a desktop, and you can do it in front of your client, or you can do it anytime during the design process. You end up with something like this, which is the Google Bayview Campus, produced by NBBJ. What's worth noting about this campus is that every single desk, every single point anyone sits in this entire building is at most 3 minutes walk from any other desk. And they know this quantifiably, because as they were designing it, they were pushing and pulling these volumes, they were manipulating all of the different positions around the campus, and every single line was being computed in real time. The reason that NBBJ actually got this job was because they were able to handle the data at the conceptual stage. They were able to handle everything that Google gave to them and say, yes, we can give you absolutely quantifiable results. We can say, yes, you want everyone to be able to hit everyone. Here's the data in real time as we're in this conceptual phase. And so that's NBBJ got that job after 5 other firms were sort of put on it and then taken off it. So that's sort of thinking about that stuff at the urban scale. We're actually going to take that down now and think about digital manufacturing. Traditionally, when you think about digital manufacturing, it's generally, or it has been, in my experience, hundreds and hundreds of one-of-a-kind components that are sort of made or a flatbed cut and then painstakingly assembled. So what we actually saw this year was kind of a move away from this kind of stuff and towards objects that are complex and through that complexity allow for a multitude of different forms while still relying on sort of traditional techniques. So this is blown by Jose Sanchez, who is a game designer and architect, and this was just a little display that he put up for the London Olympics. And this is the key thing about this is a one single object, but it can be combined into a multitude of different ways. And taking it up to an architectural scale, you have this parking structure art facade by Urbana. This is a very interesting facade because when you look at the complexity of it, each of these is just a metal panel. On one side is coloured blue, on one side is coloured yellow. When you're looking at it from one side, you see an entirely blue structure. When you're looking at it from the other, you see an entirely yellow structure. When you're midway through, you start seeing a slow shift between blue and yellow. This is made out of 6 different components that are mass-produced. So while you get an enormous amount of complexity, this is exactly the same as if you had any facade that had 6 components in an even order or in sections. And the key thing about it is that these 6 components are actually organized by the computer. So instead of saying we're going to build billions of one-of-a-kind things, you're saying, okay, we are going to use the strength of the computer, which is the organization of data, and we're going to use that to allow standard objects to be mass-produced in a way that seems like it would be impossible to put together yourself. We also see this with the Amazon corporate headquarters, again by NBBJ. These spheres, although they seem incredibly complex, there's only 3 or 4 different types of glass panes there, and there's only 2 types of steel detail that's connecting them. And this changes across each dome, the radius of each dome, but they've actually used the sort of their knowledge of parametric design to be able to simplify the stuff down to a very, very sort of set number of components. That's sort of traditional. That's traditional parametric design stuff, just sort of applied to a more sort of robust and sort of money-efficient context. In terms of the cutting-edge stuff, we're actually sort of moving away from traditional parametric design and towards simulation and towards agents. So the first thing I want to talk about is the very many. So this is the Fraxenda by the very many. The reason I want to bring this up is just to have the image in your head, and I want you thinking about how it could be built. And we're going to shift to something that's a little bit simpler. So what we have here, this is a single cast, a single concrete cast, made at, this is sort of displayed at TextFab. And so hopefully what we can do in the next slide is show how that single cast is constructed. And this is going to work. Excellent. So that, again, this is in Kangaroo, which is a free plugin for Grasshopper. So you start with a very, very basic mesh. You turn that mesh, by relaxing it through a simulation, into a tensile structure. So you know that with this tensile structure, if you pour concrete into it, it's going to maintain that form, as long as those strips sort of maintain their integrity. Because they're developable strips, they can then be laid out flat. And because they can be laid out flat, they can just be simply cut out. Come on, go away. Because they can be laid out flat. Sorry. Because they can be laid out flat, they can be produced just on a standard bed. The way this is possible is because they are developable strips. The idea behind a developable strip is that it's any double curved surface that, if you can imagine putting your fist on one end of it and pushing, if you can do that and it can roll flat, then you can obviously make it in 2D, and then after making it in 2D, form it back into the original 3D form. And this is actually how they did it. They sort of made these things in 2D, zipped them all together into a mold, and then produced this single flowing form, which they then sort of unpacked. And there's I couldn't find an image of it, but there's a larger installation of this that's about 3 stories. All of the concrete is just fine, which is crazy. It's worth noting that this is actually kind of one of the genius things, regardless of what you think of him, the genius behind Gary's designs is that they are all developable surfaces, because they're originally designed in CAD. If you start off with something flat, you cut it out, and you bend it into a crazy shape, then you know you can develop it. Normally, what we just experienced was them going the other way, getting something complex, working out how it's developable. He starts with the flat, curves it, and then builds it as though it's flat. So I just thought it was quite interesting. I hadn't considered that before. So now we go back to the very many. And what's interesting about this is that we can't actually see those strips. That's how this must have been built. It's a tensile structure. It's built out of a flat material, but it's not built in that fashion. And actually, if you look at the close-up details, you'll see that these things aren't big sort of flat things. They're these crazy interweaving, interlocking, tiny strips. So how on earth could they possibly put that together? And the answer is by using particles. So this here is a swarm simulation. This is a swarm simulation. Is anyone familiar with this concept? You just have individual tiny little birds. They're called boids in the Yid accent. And so what happens with these little critters is that they're flying around. They have certain goals. They have goals to stay a certain cluster, or stay clustered at a certain density, or to repel each other, or to seek something out. What you see here in this is that as they sort of hit a certain distance from one another, they form into lines, and then those lines start forming a mesh. So looking at that, and then looking at this, what we can see is that you can use this to interfere with a mesh. So what we're seeing here is something that you guys can understand, which is a particle is hitting a surface, and it is saying obey gravity. And that particle is then runs along the surface as water does, and finds, form finding. It finds exactly where it needs to be in order to deal with gravity. But it doesn't have to be gravity. It can be anything. So in this case, what we're seeing is thousands of little particles that run along with 2 rules. One, you have to be developable. You have to run in a fashion which lets me cut you out on a 2D plane, and you have to run along a line of tension. And so that's how these things get built. It's just one instruction, which is be buildable and be on a line of tension. And then through that, all of these things can just be assembled from 2D elements and then put together into these complex shapes.
Are the patterns repeatable?
Repeatable?
Yeah. Can you, like is the swarm, is it a random driven thing?
No, there's no such thing as random. You set a seed. You can absolutely get your results twice.
Right. So you have the same seed gives you the same result.
That's actually probably quite a good note. when you're running a simulation, there's no random results. You set a seed at the start, and that seed produces what seems like random results, but if you put that seed in, you'll get the same results. So that's actually a good thing to know about running a simulation. So part 2 is some of ACADIA's works in Timber. So this is what a traditional NURB subdivision looks like. What you'd say is, okay, here is my surface, I'm going to divide it based on a mathematical function. What we start to see here is that these panels, although they sort of follow the lines of the surface, they're not actually the most consistent things, especially when you're trying to put them together and build something. And so what you'll find is that as these things become more and more offset and weird, you actually start obeying the maths more than you are obeying physical constraints. And so what we're seeing here is a move away from that. So this kind of panelization, it's a triangulation, and then it is inverted. The reason it's an inverted triangle is so that the stress goes to the center of each panel and not to the corner of each triangle. But what we can also see is that it doesn't follow this pattern. It doesn't follow the standard pattern of towards the edges and towards the larger areas. It's going to get warped and it's going to get truncated in other areas. It's actually consistent. It fits a panel size. And it sort of fits exactly, and as you can see, hopefully in that little detail, as the curvature changes, it actually changes its form to be the inverse from that hex into a bow tie shape, and that's to deal with that curvature in sort of a more innately useful way. And so there's an interior view of that space, and this space is entirely that dome is entirely self-supporting. It's just the timber that is creating that huge span. And so how they've managed to do this is again with particles, and so I will show you this little demo. Again, this is a grasshopper thing that came out last year. This effect can be achieved after about 30 seconds of mucking around, and what we're actually seeing is as this is edited and transformed, the panels self-propagate and lay themselves out in a way that is most beneficial to the panel and not so much relying on the maths. Watching, because what we actually see from this one here is that you can start using this technique to produce forms that are impossible to do currently using our current techniques. What we're doing at the moment in NURBS-driven stuff and maths-driven stuff is you're basically relying on the equations and relying on the inputs of those equations to produce your form. This is entirely localized. As long as a point can form a triangle, you can get any type of surface you want. And so what we start to see here is these absolutely crazy, impossible to kind of visualize forms. And what we can see is that they can be edited panel by panel to be any density that they desire. And each of those things is of a consistent size and a bit easier to work with. Sorry. Let's do this again. So that's how we're doing this. We're going from a mathematical concept down to considering each panel is a living entity that is seeking out the best possible layout for itself as a panel. And what we're actually seeing this is the fair tower, and this is the number of panels and the different types of panels transforming over time as they localize themselves into optimum fits and localize themselves to sort of maximize on efficiency. And so that is a human-designed building, and each panel has said, okay, we're trying to save money, we only want 16 different types of panels, let's go from having 1 million different types of panels down to 16, 20, whatever that number is, and that'll actually sort of, that process of rationalization saves time, saves energy, but still leaves you with the result that you want. Now I'm going to shift and we'll start talking about Foxholes, which is a completely different sort of model than we're used to. Does everyone know what this is? Minecraft? Does everyone have kids who plays with Minecraft? Because this is a very, very basic tool, but the thing about it is that the fidelity of it is not set. So what we're starting to see is as computers getting more and more powerful, voxels are becoming a better and better option. The difference between what we currently use vectors. Vectors are smooth, they're infinitely smooth, you can infinitely zoom in, and you always get that curved line. Bitmaps and voxels and anything like that, they have a resolution. So that is a certain limitation of that model. But what it allows, what you can do with a bitmap is that you can say, okay, I've got zeros, I've got ones, I've got information laid out in the scale. I can actually loop around that and turn it back into a vectored image. So we can say that here, not really, but what I've got on one side is a Photoshop apple, and the other side is an Illustrator apple. The Illustrator apple is going to be infinitely detailed. The Photoshop apple is going to have gradients and smoothness and stuff to it. And we can actually convert between each other very, very simply. And so we can actually do that in 3D. So here is a process where someone has just been described as a bunch of ones and a bunch of zeros, and they've been wrapped, and from that you've had a mesh. And we could not describe this using our current methods, because you'd have to go through and draw a NURBS curve for every single element of his body, and the amount of detail that you go into would be absolutely insane. And so you start being able to get these types of surfaces out of it. So on the left, that's a sculpture, that one is a render. But what you can start to see is that you can get types of surfaces that are currently impossible to generate. And so at an architectural scale, this is just a conceptual building, probably wouldn't actually work at all, considering some of the floors seem to be rounded. But what's key is that even though this is a very busy looking building, you can put your finger on it and track the entire surface, or the entire way around the building, all the way to the top, all the way to the bottom again, and you'd find a continuous flow line the whole way through it, which is pretty cool. And it actually has a relevance at the small scale, because what we can start doing is saying, okay, this square needs to be supported by this wall. Draw the force lines that are required to support those two elements, and draw it as a gradient of one being absolutely is necessary for the force to be transferred, and then changing that gradient in order to sort of create a perfect path and the perfect shape for that structure. So what we're seeing here is that structure developing over time. Again, this is just a free piece of software that you can have with this. You can actually build that stuff in. So if this is purely under gravity load, you put any force you want and it will deal with it. And so what we're actually going to start to see, this here is a 3D printed structural joint developed by Eric, and this is the absolute optimum shape for that timber structure, for that steel structure. The key thing to note with this is that, this is according to their statistics, so I defer. But a lot of that wasted steel is the wasted steel in those structural joints being removed actually lightens the load by about 60% in some extreme cases. So being able to strip all that information away and just getting the absolute essential element like reduced steel for that load is a huge step. And what's cool about this is that considering this is the absolutely optimum load path for this structure, you actually get an aesthetic out of it that you wouldn't ever consider to be rational or logical. So this is an interesting. This thing is about that in your hand. So in terms of the fidelity, probably that wouldn't cope. But again, with your slider, all you do is you'd say, all right, thicken it up. It will thicken up in areas it needs to, and thin out in areas that it doesn't need to. So this is very, very new. This is only the last 6 months, but this test structure is going to be built hopefully in the next couple of months. This is over in Australia, and every single joint in this entire structure is going to be a bespoke one-of-a-kind system. Worth noting though that it's exactly the same piece of code. So it's exactly the same family that they're dropping into each one of those things. You're saying this joint behaves locally. It is going to be turned into a one-of-a-kind object, but the work on your end is actually just to say you are a generic joint. So the material logic evolves out of a very, very standardized methodology that you can imagine going through. So what this all comes from in my head is that hopefully there'll be a chance to return to material architecture. We're talking not about maths, we're talking not about abstract systems, we're talking about things that are developed physically, they're tested in real time, all the way up to the scale of maneuvering and changing things at an urban scale and instantly seeing the response of that. Iteration time cut down to, let's see if it's here, let's see if that works, let's see if that works. And having all your Excel spreadsheets instantly updating, all of the visual information immediately sort of feeding back into what you're doing. And one thing I wanted to leave on was 2 videos. One being this, which is Elite Motion, which is, you can buy one of these for $50, and this is it working in the current version of, oh, I've destroyed it, the current version of Grasshopper. So this is a person manipulating squares in real time in the computer by picking it up with their robot creepy hand and moving it. This is an incredibly intuitive process. I've seen videos of people plucking every petal off a virtual flower and doing it in a millisecond per leaf, because it is going back to that process of physically moving your hand and having geometry respond in real time, which we're used to. And over here is a more traditional parametric model, but combined in real time with that same kind of simulation and instant feedback. So this is sort of what we already have. But what you're starting to see is that these numbers are changing because they're not entirely parametric, they're simulation driven. So there's physics associated with this, and what it allows you to do is push a parametric model way, way further than we currently can. So you can see here, this kind of stuff is absolutely reasonable, but when you start inverting it, and because you're not relying on maths, this is an updating physical model. And skip the weird stuff. Again, now imagine that with that human hand, grasping it, twisting it, seeing how that joint works. And this here. So what I think is very important about this image here is that you've got 3 spaces, one 300 meters squared, one 500 meters squared, and one 700 meters squared. Those numbers do not change. You manipulate the perimeters, and every other perimeter element shifts slightly to deal with that. You can lock them, you can pin them, but it is a process of playing. It is a process of you making these minute adjustments in real time, having things set, having things like this has to be 3 stories, this has to be 500 meters squared, and being able to push and pull that and manipulate that in real time and getting instant feedback. And what we're actually seeing now is tools like, has anyone seen the Microsoft HoloLens? No? Quick up nerds. Microsoft HoloLens is a virtual reality helmet. Oh, is it?
I was talking about it.
Yeah. It is a hologram creating helmet. What you're seeing there on the right is someone wearing one, and the CAD model that they're currently working on is floating to their left. What you're seeing on the left is an Oculus Rift, which is a full VR headset, and that person is pushing in space, and inside the digital world, they are pushing and pulling and holding a physical cube. If anyone has used a VR headset, it feels absolutely real. Facebook has just put $2 billion into this industry. It is going to return architecture through simulation, through physically interacting with models into a much more intuitive, faster, data-driven, play-driven model. That's not from the from ACADIA. These developments have sort of been. That video I just showed you came out like 2 days ago. So this is absolutely right on what is about to be happening. An Oculus Rift is going to be $300. A Leap Motion, the hand thing, is currently available. You can buy it yourself, $100. I don't work for them. I think it's the coolest thing in the world. And so that's my own personal thought of 5 years' time, 10 years' time, is we're going to be playing with models again. We're going to be playing with models, but with all of the data-driven information laid over the top of it, so that at the conceptual stage, you can manipulate things and get instant feedback. Slight plug at the end. I work for Product Spec. We do digital design consultations. We can do workshops. We're incredibly experienced in terms of workshopping, handing out information. I want to spread this stuff as far as possible. We can make custom tools. We can make custom parametric models. We're working with brands at the moment. We're working with Wellington City Council. It would be fantastic to get some stuff up here, especially with the larger projects that Auckland has. I personally really just want to push this stuff. I think it's fantastic. It's all within everyone's grasp, and it would be a bit of a shame for us to all fall behind just because we're a tiny island and we don't get the 10,000 people firms and enormous money spent on research. This stuff is currently working at the macro scale. It is currently working at the micro scale. What we're going to see over the next sort of 10 years is more and more of the stuff working together. So making changes in the macro scale and having that rocket through right down to the micro scale, where every joint is defined by decisions made at urban planning level. So yeah, thank you very much.